Welcome to videos on linear integrated circuits. In this video, we are looking at quantization error of a A to B converter. So let us consider the quantization error of an ADC, which is a 3-bit ADC. We have code lengths given for different bits. As for 000 it is 1, for 001 it is again 1, and here the code lengths are 0.5, because we know that the ideal code lengths are 1 now it is actually less than the ideal value, and here it is double the ideal value, and here it is 1.5 LSB. Now here this is at the transfer characteristics of the ADC, which is an ideal one. Now as we can see here, the code length of each of the codes are actually 1 LSB. So this is the ideal case. In this ideal case, we know that the quantization error will be maximum of half LSB and minimum of minus half LSB. The peak-to-peak quantization error will be 1 LSB. So let us try to understand how does the quantization error can be plotted for a particular condition where we have the code lengths not an ideal one. So if it is 1 half LSB, half LSB, and 4 half LSBs, and there is a 2 LSB code length. Now let us try to identify how do we find out the quantization error and what is its effects on the output of the ADC. Now we know that this is a quantization error what we considered in the previous slide. So let us go bit by bit and try to find out what is the code length. I can see we are considering the first code, that is 000. So we are assuming a code length of 1. Here, since we are considering this is actually half LSB. So since it is 000, so we are considering another half as a reference here. So this is actually half LSB, but effectively it is 1 LSB, because we are taking 0 as the reference, and another half LSB will be there before this 0. And since it is the estimation is proper, there is no error when the input voltage is 0, so that's why there is no error. But we'll be underestimating the input voltage, which is 1/8, so that's why the error will be minus half LSB. This is actually minus half LSB. Now the next bit is actually 001 has a code length of 1. I can see, so there's a output is making a transition at 1/8. Now it is having a length of 1 LSB. Now we know that here we have actually underestimated the code, the input voltage. Now here actually overestimating. Now actually the code is actually 001. So there's the overestimation of half LSB. The estimation, the error will be 0 when it is 1/8 over here. So this is actually 1/16. At 1/8 it is there is no error. So, and again we are underestimating the bit with the input voltage as 3/16. Now I can see here the code length is 1 LSB for 001. The next code length is actually half LSB. So let us try to see how it is looking. Now you can see this is an half LSB code length. The output is making a transition from here to here. Now since it is half LSB, now the estimation is we are actually overestimating over here, and it is there is no error in the quantization. The quantization error is 0. Next, what happens is, since this is only code length is half LSB, the next value will change immediately here. Now this black color is actually the ideal one. Now this red is the actual one, which is representing this half LSB. Now here red and black are coincided. Here also red and black are coincided. Here also red and black are coincided. Now till this point it is the ideal value. Black is actually the ideal value. I can see for this 011, the code length is only half LSB. Here also it's only half LSB. It's making a transition from 010 to 011 here. Now we can see the error was actually 0 here. For this input voltage, the error was 0. But any input voltage slightly greater than that, we are actually overestimating it by 1 LSB. So that's why I can see the error actually increases by 1 LSB. So the quantization error is more here, and we are still representing the input voltage from this 2/8 to This is actually 2 by 8 is 4 by 16 to 5 by 16. The value is the representation of the output voltage is 0, 1, 1. The quantization error is maximum here, and that quantization error will reduce. It will not become 0. It will become half LSB over here. Now we can see this is what is the code length of half for the second 0, 1, 1. Now you can see since it is only half code length, for the next input voltage anything slightly greater than this 5 by 16, output again changes to next. You can see now this black one is the ideal one, but actually the typical one as per this code length. Now the output changes from 0, 1, 1 to 1, 0, 0. Now we can see the error will going to further increase. This was actually the error at this point, which is already more than the previous the ideal value. Ideal error would have been here. So compared to the ideal value, the previous bit itself has an error of 1. Now since we are having only half code length, so this error is further increased. Now in the ideal case it would have gone down to 0. Now it is the typical error is now more now. So now if it is further increased, when the input voltage is further increased, we still have now this is first half LSB, this is second half LSB, this is third half LSB, this is fourth half LSB. Now you can see the error is keep on increasing because we are overestimating the input voltage by half LSB. So that's why the error is keep increasing by every time whenever the input voltage increases. Since the code length is small, the quantization is increasing by half LSB. Just a minute. So we are here. So now we are gone to the third half LSB, that is this one, that is now it is 100. So it is again making a transition at this voltage, that is now it is going to 101. So 101 is also half LSB code length, half LSB code length. From that onwards you can see the actual code length is actually 2 LSB. Now you can clearly see the quantization error reduces by almost 2 LSB because you are representing the input voltage from this happens to be this is actually how do we this is actually 1 by 16, 2 by 16, 3 by 16, 4 by 16, this is 6 by 16, this is 8 by 16. From 7 by 16 to almost 11 by 16, the output representation is 110. So we have a code length of 2 for an input voltage ranging from 7 by 16 to almost 11 by 16. So that's why since we are representing for this entire range of input voltage by a same code, that is 110, the quantization error has reduced. But it is still more than the ideal case. The ideal case could have been minus half LSB. Still we have an error of half LSB plus half LSB, which is more from the ideal value by almost 1 LSB. To represent this 7 by 16, this is 5 by 8. 5 by 8 is actually 10 by 16. Now this happens to be 11 by 16. So 11 by 16, we have a quantization error of almost plus 1 LSB. Suppose if we further increase the input voltage, now here we again have a overestimation. The error increases, and error comes down to the ideal value as the bit length of the last one is 1.5 LSB, because this code length merges with that ideal value. Here finally the value becomes merged with the ideal value. As you can see here, the quantization error is in the ideal case it was not exceeding plus half LSB and minus half LSB, whereas in this particular case for a code having different code length, so the quantization error has gone up to plus 2.5 LSB. Whenever we have a larger quantization error because of this reduced code length, so we're going to have a lot of error in yeah, of course the signal to noise ratio will be reduced, and it is fortunately that we are not missing any codes. The missing codes are not there because we could able to recover back the codes even though it is half LSB 4 times, and those half LSB 4 times is then compensated by this 1.5 and 2 over here. So that's why we're not missing any codes. Even though the codes are not missed, we have a large quantization error because the quantization is going up to almost 2.5 LSB, of course, as compared to the normal half LSB. So this way we can able to understand the quantization error plotting. So with respect to the code length in terms of LSB. So this is the black one indicates the ideal code length. So this is the typical code length. So the typical code length is in this particular case it is 1 LSB. Here it is again 1. So here also it is now it is, you can see it is only half LSB and it is making a transition here. It is again half LSB making a transition, another half LSB. It is making a transition, another half LSB, and it is making a transition. Now it is 2 LSB. After 2 LSB, it again makes a transition and it is now 1.5 LSB. Ultimately, this catches up with the ideal value. So that's why we have this error also catching up with the ideal value. So this dotted line indicates the ideal quantization error if the code lengths are equal to 1 LSB.